So to open this up, I went to Help, Example Models, clicked on How-To Models, and went to SIR Agent-Based. And when it loads, you'll see this structure over here in what's called the Projects window. Does everyone see that on the left-hand side? Yeah? Okay. In the Projects window is depicted the structure of an AnyLogic model. Now, in this case, that structure consists of three major components. One is a depiction of a person, and I'd like you to double-click on person, and we will actually see a theory of personhood with respect to this model depicted. This sort of captures what it means to be a person in this model over here on the right-hand side. And we'll be discussing what this diagram means. It has a very precise meaning, in a meaning that will get more specific as we delve into it and look at properties of these components, but it describes the theory of personness or personhood. There's also what's called a main class, and this is going to depict sort of features related to the model as a whole. This is the stage in which these people will strut. This is the environment in which these people will live. And if you scroll over to the left-hand side, as is often done here in the so-called canvas window that depicts things, you will see the characteristics of individuals and some information maintained on, say, the number of susceptible, infectious, and recovered people over time, and in fact, the population of people. We'll be spending quite a bit of time in our main class later. This will be where we accumulate statistics across the entire population, for example. It will also be a place where we might simulate some dynamics of environmental context, which might be relevant for shaping the evolution of agents. Finally, down here on the lowest part, there's going to be this X, which stands for experiment. And the experiments are going to be the place where we run scenarios with the model. So we're going to use experiments to ask what-if questions with the model. And an experiment in order to do that, it's going to incorporate our assumptions about the scenarios. So if we go over here and we click on that, you've seen this over in the Canvas window, there should be another window called Properties. If you don't see it, you should be able to go up to View menu and choose Properties. But Properties will be there somewhere. Now this is the AnyLogic interface, and it's an interface based on a platform called Eclipse, which is a very popular software development platform. It is reconfigurable, and as time goes on, we'll learn how to manipulate these windows. For now, we'll try to leave them in their current positions, but soon enough we may be repositioning them or zooming in on them. But you'll notice this given simulation represents a scenario with the model, and if you scroll down here in the properties, you'll see assumptions being made associated with that scenario. For example, what the illness duration is, the contact rate to assume, the probability on a discordant contact, a contact between a susceptible and infective, what's the chance that the infection is transmission in an initial total population. If you're using AnyLogic PLE, you'll want to download that version of this model where the total population is less than 250,000. Okay, it needs to be less than 50,000 for PLE. Okay, so having done that, ladies and gentlemen, I would like to go talk a little bit more about what this model involves. And we're then going to run this model, okay? So let's go double-click on person. So this model is going to depict stylized individuals. They could be people, they could be animals, which exist in one of three states with respect to their infection status. Those three states are depicted using what's called a state chart here. So an individual can be susceptible, infectious, and recovered with respect to this particular concern as captured by this state chart. In this case, it's clearly a natural history of infection. Now, betwixt those states, at a given time, a person's going to be in exactly one of these states, and betwixt these states are these transitions that indicate processes that bring an individual from one state to the other. And as you'll see, there's an infection process and recovery process. And if we go click on recovery, you can go see that there's some assumptions about the nature of that recovery process. For example, in this case, it's classified as a rate transition. There's a broad choice of others that you'll soon be familiar with. And there's a rate here that's given. It's a hazard rate, for whom that's a meaningful concept. It's a biostatistical concept. It's a probability density, a chance per unit time someone will recover as 1 over the average illness duration. And assuming that, a chance per unit time of recovering of that means that on average they'll spend average illness duration amount of time in an infectious state. Okay, so these individuals are going to go through these 3 possible states. And you'll notice right now it's a linear transition. You'll soon be changing that. But for the moment it's a linear transition process here, from one to the other. The infection here, the infection transition is going to depend on contact here. And this contact is going to be communicated by something known as a message. And before the day is out, you'll be creating your first messages and sending them within these models. Okay? So we have this kind of natural history of infection illustrated for a person. It's important to note that each state chart depicts a certain set of concerns, a certain type of concern. There may be multiple state charts for different types of concerns. For example, we might have susceptible infectious recovered with respect to this, and there might be another state chart for the treatment regimen which this animal or this person is subjected to, or there might be another state chart to having to do with their diagnosis status, etc. So we use state charts to illustrate classifications of an individual and their evolution over time. So it classifies the state, and it classifies transitions in that state, or actions that affect that state. Now, these people are not going to exist in isolation. As is illustrated by the fact that they can be infected, they are going to be placed in a context. And if we go up to main, this is going to capture that context. So double click on main here, and it will show in the canvas a depiction of that context. And you'll notice that there's this population here of people. And if you click on that population, you will see in the properties menu something that is going to illustrate the features of that population, including what its total population size is. But ladies and gentlemen, you will also notice that that within here we can define statistics, and we'll soon be defining statistics over this population, which will characterize the status of that population at a current time. Okay, so this is going to be the population in which those people circulate. If you go up to main as a whole here, to the main context, this again is the stage in which the agents strut. It's where that population lives. But if you go to main, you will notice that by scrolling down here from the top down to the space and network area, you will see information about the space in which this population of people is embedded. How broad that space is in terms of sort of physical width, also in terms of logical width, how it's divided into cells, and then how individuals are placed in a context with 8 neighbors. That is, neighbors to the north, southeast, and west, northeast, southeast, southwest, and northwest. Okay, they're given 8 neighbors within that context, and they're placed in this arranged grid. Okay, so ladies and gentlemen, having seen this depiction of a person, and seen this depiction of the space in which those persons are embedded, we are going to now see the logical consequence of those assumptions. This model has characterized some assumptions about states a person could be in, about how they recover, how they get infected, about the space they're in, and yet the implications of those assumptions are hard to play out in our heads. It's hard for us to reason reliably in the context of so many details and so much interaction between those details. to understand the logical implications of a theory of personhood like this, we are better off using a simulation that will play out those consequences in a consistent fashion, in a logically consistent fashion. To do that in AnyLogic, you right-click here on the simulation and say Run. Okay? That will run that particular simulation, that particular scenario, which involves those sets of assumptions. Now, I'm going to ask you, ladies and gentlemen, I'm going to tell you one additional detail, which I didn't stress, which is that these people are going to be in this large space, 250,000 individuals, and one individual within that space is going to start infected. What do you think will happen over time in that context? If you were to guess, what will happen? What do you think will play out over time? If we start one individual infected, the other susceptible. What might we see visually?
Other people will become infected?
Okay, good. Other people will become infected, and will they all suddenly, the entire space suddenly turn infected?
No.
How will that infection play out spatially?
Wave-like spread?
Okay, wave-like spread. It will spread out in a ring, and that's exactly right. So if we run here, what we will see is a large space, and the individual is starting infected, and the infection is spreading out. You'll notice here that we have three colors. A color yellow for susceptibles, a color red for infected, and a color gray for those individuals who are covered. Those happen to be consistent with the colors used in the diagram here, although, as we'll see, they're imposed via a different mechanism. So as we zoom out, we'll see the infection spreading, and you'll notice there are some controls up here. You could press this one, for example, to pause the simulation. And as the simulation plays out, you'll notice a couple salient features. First of all, as was noted, the infection spreads. In this case, it has a long enough duration that it has a chance to spread before dying out within an individual. And so there's some spread. That spread is localized. It's spread to neighbors in space. And as a result, it goes in a sort of ring-like structure. And that ring is spreading. But the ring has irregularities. These irregularities are due to the vagaries of chance. Who happens to get infected and at what time from their neighbor, etc. And as a result of this kind of ragged edge, but its shape is unmistakable. It's spreading up in this kind of ring-like fashion. And if we were to run this out, we will see the infection continue to spread here over time, and it'll eventually reach the end of the space and complete. You'll notice also here are counts of the number of people susceptible, infectious, and recovered over time. And we can, of course, chart those out. Those are aggregate measures being totaled up across this population of individuals. And it's important to note, although perhaps obvious once one has been in the field long enough, but important to note that aggregate measures can always be computed from a more detailed underlying population. If we have a underlying population divided individuals, we can aggregate up to get total measures, cross-sectional measures like the number of people infected over time, etc. But we also follow individuals in their history, their biography, and we can go down and look at where those individuals infected, the spatial patterns associated with this. So we're running this here, and shortly you'll be adding your own experiments to examine other what-if scenarios. Okay, so the infection is spreading. We have a large bulk of the individuals being recovered now, some individuals being infected, and some individuals who are susceptible here. Okay, so ladies and gentlemen, having run that out to the edge here, I'd like to stop this model. And we can do so using this button here, this red button. Alternatively, we could go back to the main AnyLogic window and press this button here. Okay. So we've just run this model out. We've seen some features. I'm going to ask you to make a few small tweaks so that the model will run more efficiently and with greater insight. Specifically, what I'd like you to do, ladies and gentlemen, is, again, making sure the simulation is clicked here. I'd like you to go over here to the right, to the Properties menu, and I'd like you to go down near the top, and you'll notice it says maximum available memory. I'd like to actually set that to a larger amount. I'd like to set it to 1024. It was actually starved for memory there, and that's one of the reasons it was running slower. It was doing a lot of work to free up memory. So it'll run faster if it's up at 1024. So one gigabyte of memory associated with it. Secondly, ladies and gentlemen, I would like you to scroll down to this area where it says Window, and I'd like to enable a couple things here. One thing is enable panning, and I'd like you to enable the, there should be time model navigation should be here. Okay, we should do this one, and then time scale should be selected, as should model time down here. Are you following that okay? Should I give a bit more time? How did I get here? I went to simulation. I saw in my properties window the properties of the simulation. Here I changed this to 1024, and down here I scrolled down to window and I checked enable panning, and I went to made sure time scale was set up. I checked model navigation and model time here. Okay, this will let us get some additional insights from the model. Okay, having done that, ladies and gentlemen, I would like to now rerun this model, keeping track of some features to see how long it takes to actually get to the sides. So I just ran that again. How did I do that? There's several ways to do many things in AnyLogic. A given action often has several ways to accomplish it. My favorite way to run is to right-click on the scenario you want to run and choose Run. But there are other ways, such as through this menu here, and you can also do Model Run here and choose which one you want to run. Okay, so I'm going to go back here, and now with those changes being made, we're going to have time presented, and we're going to be able to explore this model while it runs. So I'd like to run it, and I'd like to ask you, please keep track of how long it takes for this to reach the upper edge. You'll notice time is coming out. Now, I'm going to pause this model for a moment and show you a feature. So I'm going to pause it, and you'll notice that there's this navigation menu here. With this navigation menu, we can dive down and see for particular individuals what their status is. For example, here's an individual who's recovered and an individual who's susceptible. Here's another individual who's recovered and another one who's susceptible. By scrolling here amongst individuals within the population, we can browse the status of those individuals. We can get some sense of the individual stories that underlie this overall picture of the model, that underlie these aggregate statistics. Okay? So I'm going to continue to run this model here, and we're going to notice the time at which it hits the boundary here. And that time is going to be one we keep in mind when we do some comparisons with alternative scenarios. So I'm running it out now, and you'll notice that it gets the boundary about time 300. At least on mine, it's time 300 or so. Okay? Okay, so ladies and gentlemen, we can stop this model now. Let's stop that. And now what we're going to do is we're going to modify the model. We're going to ask some other what-if questions, okay? First thing I'd like you to do is to right-click on simulation, this experiment, right-click on it and select copy, okay? we're going to make a copy of it with all those settings that we changed, so we don't have to reproduce that every time. So right-click, copy, and now I'd like you to right-click on the model as a whole and click paste. This will create a new experiment. This experiment will allow us to conduct new what-if questions, new scenarios that have different assumptions behind them. So for this scenario, if we select it, we should be able to go over to Properties window, and I'd like you to go and go set this to be to have a name, which is going to be long infection duration. Okay. Now we could call it infection duration. You know, this is kind of I'm going to call it infection duration 50. Long leaves a lot to guesswork. I'm going to call it infection duration 50. And down, in order to realize that, what do you think we need to change here? If we were to look at infection duration 50, which of these assumptions would we need to change to have a duration of illness of 50 days? Average illness duration. So let's change that to 50. You'll notice when it changes it, it highlights it and it embolds that. What that's an indication is that you've changed the value from the default. You'll notice here that you can also specify the units. If we wanted, we could specify it instead as 7 weeks, for example. But we're going to keep it as days of as the unit here. Okay. AnyLogic is a platform which keeps tracks of the units of things and can confirm unit consistency for certain types of modeling. Okay. Which can be of great value in making sure you're not doing something silly like adding the number of deer to the number of people or something like that. Okay, so 50 days is the average illness duration. How do you think this will affect what we see over time? Okay, people have the infection for a longer period of time before they recover. How do you think that this would affect how quickly that infection spreads in the population? Each infected individual, before they recover, they're going to be infected for longer. Do you think they'll infect more people?
Yes.
Okay, so they might infect more people. They're infected for longer.
Just as infectious as it was before?
I'm sorry?
Yes.
Is the agent still just as infectious?
Just as
it was
infectious,
before?
yes.
All right.
It'll go through faster. Yes.
Okay, so the infection probability per discordant contact, per contact between a susceptible and infected, 50% probability of infection. How do you think it will affect the, so do you think it will spread to the border quicker? Do you think it will spread? Okay, and how do you think it will affect the visual appearance? Well, we're going to have a thicker ring, all right?
Yeah, it'll go to each border quicker.
Okay, so there's going to be a thicker ring around this outside here. You notice they're staying longer on average. There's this kind of larger periphery. Now, I'm running this at full tilt here. This is this mode here, real time. We could actually slow it down if we wanted to see it play out in a more stately fashion here. We could actually, you can get out of this virtual mode and slow it down, control the speed if you want to do so. So here we're seeing the events occurring at a very microscopic level. But in the interest of time, I'm going to play it out at full tilt. Okay, so it's spreading out. We can keep track of model time down here, and we're passing time 200 here on mine. We've still got some people infected way down here. Why is that? These people are still infected, even though they were among the first infected. It's time 200 and they're still infected. Why is that? Well,
There's a distribution with the hazard rate?
There is. So this has this is a hazard rate, meaning the time spent in the infectious state is actually not a fixed constant. it's actually drawn from an exponential distribution. It's exponentially distributed residence time, as we say. And as a result, you know, some of those are in there for longer and some for shorter. Okay, it's crossed here at time 298. It actually didn't seem to speed up the time it took to get to the border. How could that be? People infected for longer. You'd think they're infected for longer, they're going to infect more people, and therefore it's going to spread faster in the population. What part isn't adding up here? Think about how it spreads in this very structured pattern of sort of contacts that are occurring to neighbors. What is it that's meaning that it actually doesn't get to the side appreciably faster? What is it that could explain that?
So, yeah, local depletion of susceptibles.
Local depletion of susceptibles. That initial time of 15, that was enough to actually saturate those in the environment. You saturated the people around you with 15 contact duration. Now you're infected for 50 time units. You know, you're going to be casting your infection at stones. You're not going to be spreading it. Your infection is going to be sheddable. If you're shedding, it's going to be spreadable. But the people around you are not going to be susceptible anymore. As a result, it's not going to appreciably change the time until it reaches the periphery. It's already at a saturated level. Okay, so ladies and gentlemen, models help us reason through the consequences of our assumptions more consistently, logically, and thoroughly than we can do purely in our head. In our head, we're really great at certain types of analyses, but when it comes to adding up all these details in a totally consistent fashion, this is what computers do well. There's lots of things computers do horribly, but this is one of the areas they excel. So we have kind of a theory of personhood, a theory of what it means to be a person and to get infected in this model, and the model simulation environment will allow us to ask what are the logical consequences of that and play it out over time. But let's not stop there. Let's run a couple more scenarios. So ladies and gentlemen, let's build those fledgling muscles you're starting to build up. So I'd like you to do another copy just like we did before, okay? So you can copy this baseline simulation. Probably we should call this baseline. Let's select this. So someone tell me. Increasingly, this is going to be interactive. I hope that doesn't cause anyone to run for the door. So you're going to tell me, how do I change the name of this simulation? I want to change it to be baseline. Right now it's just a simulation, which is a singularly opaque name. I want to change it to baseline. How do I change that? Where do I go in AnyLogic to change this name?
Right.
Okay, I go to the properties here, and I can say baseline. For some cases, I can actually right-click and do rename too, and this is one of them. So that is a nice way to do it. A general way to do it is to go to properties, and you can change it to baseline. Okay. Okay, I want to copy baseline. I want to do right-click on it and do copy. Another way I could have done that is edit copy. And I want to go up to the model as a whole and do paste. And now I'm going to say infection duration 10. Okay? Here we go. So infection duration 10. Remember, the baseline was 15. Okay? I'd like to run this. An infection duration 10.
Are we changing the duration?
Oh, thank you. Man, thank you. Interactive. Great job. Duration 10. Okay. 10 per day. You notice they have a contact rate of a certain number per day. This is a hazard rate of contacts. We'll be seeing how that's accomplished in just a minute. Okay. So let's go run that. Okay. So we're running it out. You notice this is running. It bears note this is running in continuous time. AnyLogic does have an option of doing discrete time, as is the more traditional agent-based modeling practice. With discrete time, going in time steps that are are in lockstep across the entire population. But AnyLogic has the option also of doing continuous time, and that's the default. And it turns out continuous time has some very material advantages over discrete time, which we can talk about, in terms of just brokering the different types of events. So we've just run this out. And you'll notice it actually spread a lot faster. Does anyone notice something different about the results? It spread, and while it was spreading, let's go back and illustrate this. While it was spreading, we had a thinner ring around it than we did previously. There's fewer people that are staying infected for a long period of time. And it turns out that has a very material impact on the speed with which it simulates it. It gets to the border almost at the same time. But does anyone notice anything different here? I should have provided a free set of binoculars for my boot camps. But does anyone see on their own screen something a little bit different?
Not everyone gets infected.
Not everyone gets infected. There are these occasional susceptibles there. Do you see that?
Yeah.
These small isolated individuals that in fact didn't get infected in time. In fact, here's a little cluster of them, I think. So those are reflection of the fact there's some susceptibles remaining, 12 of them in mine here. Now, you may ask very reasonably, if we ran that again, would we see the same thing? Let's go run that again. And I'm going to run it out here. And here we go. So it's running out, and this is looking familiar. These two guys here and one up there. So we're going to run this out, and we'll see. Okay, how many remain susceptible? 12. It's the same number every time. But we're seeing vagaries of stochastics. Well, it turns out that AnyLogic's default, for better or for worse, I personally think for worse, is that if you scroll down in the properties of the simulation, you can dictate whether the simulation is run with what's called a fixed seed. That means that every time you run it, it's going to give exactly the same results, assuming you have the same model, the same inputs to that model, it's going to give the same results. Or is it a random seed? In other words, is it running it each time with different vagaries of stochastics? In other words, fixed seed is you want all the stochastics. Well, they look stochastic. They're playing out in exactly the same sequence. If you give it the same model and the same inputs, it's going to give exactly the same results, even down to the point that all the so-called random actions are the same. Random seed will actually let it vary from run to run. So I'm going to run it with random seed. This is a good thing to know about. Run it with random seed. And now we'll see actually it appeared in a different area in the first place, right? And we will see somewhat different stochastics associated with it. Who's getting infected at what time is going to be different because the seeds are different. Okay.
So is that then basically an independent iteration? If you were to
That's right. It's a separate realization. It's a different replication. They're independent of each other. We can describe, and here, there happen to be 11 over. And in general, if we want to secure conviction as to the impact of a given scenario, it behooves us to run it often many times, a so-called Monte Carlo ensemble. You run it perhaps 100 times or 1,000 times, depending on your stochastics. You might use non-parametric statistics to try to establish the likelihood that the scenario, this intervention significantly reduces the burden of infection compared to the baseline. And we'll run many replications of it. So are you set up in terms of finding this model? Do you want me to describe how you get to it?
No, it's okay.
Okay.
Yeah.
Okay, because you can do help, example models, how to, SAR, agent-based. You don't need me to show you? Okay.
Thanks.
Okay, yeah, you bet. Okay, so ladies and gentlemen, we've just run those scenarios. Now I'd like to run another scenario. I'd like you to copy and paste, and this one is going to involve, so this will be infection duration 5, and we're going to change the average illness duration to be 5 days. Okay? Okay. And we will run this with 5 days. And what do you think will happen here? So I've just run it. And it's telling me it's time infinity and it's finished. Okay, that's interesting. Let's try that again. Infection duration 5. Okay, it's setting up. And here it is, it's spreading. Okay, this time quite a bit spread, but there's quite a bit left over there. Let's try that again. And I will want to make sure, ladies and gentlemen, that we're using random seed in the random area of this. Just make sure you're using random seed, so that each time it turns a new leaf, as it were. It's a different ball game. It's independent realization. So I'm running this here, and it's running out. And once again, we get a lot of susceptibles left over, comparatively speaking. We could run it this time, and most of the times it seems to spread. There'll be the occasional time, like this one, where nothing happens. Why is that? What happens at these times where it's saying infinity? What do you think happened? I'll give you a hint. There's one recovered person. Everyone else is susceptible. What happened?
They don't make contact.
Yeah, so they're making contact, but they don't transmit it. There's this, or they don't make contact. That's true. It could be either one. Was that Ned? Yep. So they have a contact rate of 1 per day. So it is, that's a hazard rate. It is possible for those, over the course of their illness. Their illness was an average of 5 days long, but it's exponentially distributed. Maybe theirs was 3, and maybe over the course of those 3 days or those 2 days they were actually infected. They didn't make contact with anyone. Or maybe they made contact, but the probability of transmission was sufficiently low. They actually didn't infect that person, right? Yeah.
So this is like SIV becoming HIV in that sense, like depending on the route of transmission, you don't have either the right kind of contact or it's not right. So this is really realistic for kind of the emergence kind of discussions.
Right. So here, yeah, there's it can capture the vagaries of those stochastics. This time it happened to catch. This time it didn't catch. And of course, what may play a role in that in an HIV context is whether the person knows, for example, they're HIV positive.
Right.
It may affect their risk behaviors, etc. Yeah, there's stochastics here associated, particularly during the acute phase when the viral load is very high, right? So, ladies and gentlemen, a model like this captures stochastics. And in contrast to compartmental models, which I work with a lot, I do quite a bit of mathematical epidemiology, and in those contexts, you're dealing with an R0, the average number of people infected by, your index infective in an otherwise susceptible population. Here, in the context of the stochastics, you really need to consider, what is the probability that actually it will catch for those first couple people, particularly. Yeah.
So question. So many of us, I think we've gone towards the R0 because there's so little that we know about, like the viral dynamics and the infectivity kind of stuff. So do you have to have that? Can this only be done on ones where it's well described and there's good, laboratory data, or do you just deal with that in your parameters, or how you set the boundaries?
So it's a great question. If you had other agent-based modelers here, they would probably give different answers to this. I'll tell you my answer, okay? And as someone who goes back and forth between these two very insightful types of lenses, from my perspective, models are learning tools, and models like this, there's no question that they can, articulated agent-based models can really flourish when we're in a data-rich environment. And this is one of the reasons why we spend so much of our time doing mobile device data collection now and so on, to really inform previously undermeasured behavioral components that are valuable in the model. And you could do similar things with animal collar studies, et cetera, I suppose. And some of my colleagues do that. but even in a data impoverished environment, I still believe that articulated models can yield a great deal of certain types of insights. And I agree with you completely. Are not, I mean, it's something that can be measured empirically, right, from the rate and the rise number of individuals being reported as infected, or number of animals, etc. You can do estimates of that, and it can allow for some wonderfully powerful analyses with a small bit of data. On the other hand, an articulated model like this can help you identify those cases where that sort of aggregate analysis is going to be meaningful and where you have to be cautious about it. It can help you identify sample sizes that might be needed to give reliable results by using these articulated models as, for example, as synthetic ground truth. You can have, and it's kind of similar to, I've forgotten your name. Peter. Kind of similar to the idea Peter has of using models like this, for example, to shape surveillance strategies. If you have a model that depicts some hypothesized situation in the world, even if that model is an imperfect representation of the world, you can often use it to spot big gaps or vulnerabilities in analyses that you wouldn't otherwise be able to easily recognize, because you use this model as this kind of synthetic ground truth. That it presents the evolution of a population whose state you know entirely, and you can then use more aggregate approaches, say with estimates of R naught or something, to estimate what's going on within this model, how many people are susceptible, infected, recovered over time, using a compartmental model. And you can check by comparison with the synthetic ground truth how far off that aggregate analysis will be with the sort of data that's available empirically.
So that's good to know. I mean, because I just want to make sure I'm not crazy, because it's been my experience, through 15 years of playing with people, is we like to do this, and when we give up, then, no offense to the disease ecologists in the room, then we start playing with R naught and some of the things that combine and are surrogates, in my opinion. So that's, am I hearing it's that I'm not crazy when I think that way? I realize that's not.
Well, let's put it this way. I actually think that both of them are lenses that can be used together. Even in a data-rich environment, we will sometimes do compartmental modeling, if only to develop our intuitions and to cross-check these models to make sure we're not fooling ourselves, to understand why certain aggregate measures might be yielding different findings or conclusions than what we see in these models. So, for example, during this week, if there's interest, I might present some of our TB models, where we for years have had compartmental models running alongside agent-based models, and each shed light on different types of factors. Compartmental models often put together in a rough and ready situation for certain types of analyses, which are then followed up by, at a deeper level, the agent-based models, but where the agent-based models can help us take that analysis further yet, and make it more refined. Compartmental models, I think, often give you a sense of where you can intervene very effectively, but agent-based models, how to intervene, the micro details of, under what conditions you will use one therapeutic strategy or another, under what conditions you'll use for prioritizing your vaccination rollout or for delivering your antivirals based on a person's history, which there's not going to be a capacity to easily capture that in a compartmental model. So I think a lot of the how we look to these models, a lot of the sort of where we often will look to compartmental models, and we use them to cross-check each other. And so I don't really think of one as obsoleting the other or as replacing the other, so much as they're used for different types of questions. And there are some contexts where we as yet lack the empirical evidence for us to, with confidence, build this sort of model, and we'll use this to build an understanding of theory building, as it were. Because models like this can be used for theory building as well as theory extrapolation. And my colleague Ross Hammond at Brookings likes to emphasize those two different roles that models play. And it's a very good point that, in theory, building models like this can be used to kind of build up our sense about what may be going on under the covers that we're not picking up, with those aggregate numbers, but which might be driving those numbers and can help us make sense of more detailed data when it does arrive. So those are just some comments.
Yeah, no, thanks. That's,
Yeah.
that's great. Those of you who work with Megan, she ran smack into this in her PhD. If you've talked to her about it with the Serengeti stuff, when they were doing rabies versus distemper, and all of a sudden she had no data on things like hyenas, and so it's an interesting conversation for your lab in that sense.
Yeah, but it's also similar to what you're trying to do in the biosecurity intervention strategies.
Oh, yeah. We have very little data on anything. We don't know how the virus is moving. We don't know what potential pathways. Well, we know there's a big list, but we don't know which ones are more likely than others. So.
Yeah, so you're using the data from this prior outbreak, the spring outbreak of PyPath, to use that to say, okay, based on the patterns of disease introduction, what could have caused it?
Interesting.
The reverse logic to what we usually do, which is interesting.
Yeah, I'd love to chat more about these things. And I know Kurt, my TA, has also worked a great deal with ABMs and has also done some aggregate modeling. He might have some good comments on this. Okay.
If there's time, this group would benefit, I think, greatly, all of us, from if you've got long-term, looking at TB in parallel fashion to the strengths and weaknesses, or which informed what, that would be, I think, really useful for this group.
Good. Okay.
So that's what we're interested in, is find the best way to either design or predict or manage.
Right.
Advanced management.
Right. Yeah, I'm happy to present some case studies on that, and Kurt was involved in some smaller aspects of that work too that he could also comment on. Frankly, I'm also happy, in groups like this, I'm happy to share our research models so you can see what they look like and et cetera, and get a sense of how we pursued particular subcomponents of it. In a way, I can't just put them out there. For the sake of my collaborators, I can't just put them out on the web, as I usually love to do. Okay, so ladies and gentlemen, I'd like to now take this one step further. So we have been undertaking some tasks that are very common tasks in a team project. I think a very important part of motivator for us to use modeling like this in AnyLogic is to be able to share models with people who are not modelers but wish to partake of the modeling results, to the point that they want to actually run and interact with scenarios, ask what-if questions. And in our boot camps, we try to speak to both types of individuals. And the tasks we've been undertaking here are common what-if tasks that someone might undertake, even if they're not going to build up the model. They can go and inspect and look and see what some of the assumptions are, and they can run some scenarios with different assumptions in place and see the results. I'd like to now take this one step further and put in a change to this model, a change that's not going to be merely one of numerical assumptions, but one involving the structure of the model. We're going to change the natural history of infection that's hypothesized to apply in this case. And we're going to ask, what would be the consequence of assuming waning immunity for this model? Okay? So, ladies and gentlemen, I would like you to now go to something we haven't used yet, and that is the palette over here on the left-hand side. Okay? This palette will have many different sub-features, and we're going to go down to this one that's called Statechart. Okay? The actual mechanisms we'll be using are also, in this case, in the agent palette, but we'll use Statechart. Okay? Now, Statechart provides the building blocks used to build this up, and we'll be using it a great deal during this boot camp. And I'd like you to go click on transition and drag it over. And you will see this drag over into the window. And I'd like you to drag this. You can watch how I'm doing this. I'd like you to drag the arrow that it's heading from. So the arrow is going from a point to a point. For the from, I'd like you to drag it down to recovered. And for the to, putting aside aesthetics for the moment, I'd like you to drag it up to susceptible, like that. Okay? Now you'll notice that it crosses infectious, and we'll be doing something about that in a jiffy. Okay. Okay, so drag it up to susceptible. Okay? Do you folks still use Jiffy down here in the US?
I do, but I'm old.
Okay. I'm teasing a bit, because actually the younger people in Canada look at me.
Well,
What's a Jiffy?
I'll just simply say that you've aged better than Dominic and I have.
Think not. Ladies and gentlemen, were you able to get that connected? I want to highlight a very important thing. When you connect it, you'll notice it should turn green on both sides. That green means it's actually connected. If you have a near miss, it may be close enough, it looks connected, but if it's not green, it ain't good. Green is good, okay?
I can't tell if it's green or blue or light blue.
Okay, yeah, it's not white. Okay, next, I'd like you to double click on that. Let me rehearse that again. Double click on that arrow, and then you can drag it to exhibit a shape of your choosing. Okay, so might be something like this. How did I do that? Well, in order to, I'll undo it here. In order to do it, I double click on the arrow, and you should see a little handle appear. And you should be able to drag that handle to the appropriate point here. Okay? Do you folks, is that okay? Were you able to do that? Okay. So we've just added a transition, ladies and gentlemen. And now what I'd like you to do is to put in an assumption about that transition. Okay? And the assumption will concern the process involved in shaping that transition. Okay? So specifically, I'd like you to call this, the name of it should be waning immunity. So remember, state charts encode the states, but also the actions that change states, the processes over time that change states. This will be a waning immunity process. And it will be associated with and we're going to make it a timeout of 150 days. Okay? 150 days. Now, you'll notice we could have made it a rate, a hazard rate. That also would have been a chance per unit time. But we're going to make it a fixed amount of time of 150 days. Okay? Okay. 150 days here as the timeout. Are you ready to run this? Okay, to run it, we're going to need to go back to, well, one way is to go back to projects. And you'll notice that this change, it's going to apply for all of these scenarios we've been running. So let's run the baseline scenario with it. What do you think the impact of this will be, of making that one little change to things? How do you think that will affect things for the baseline? Well, let's run it. Do you see anything different? Anything different? When do you think you'll start to see something different? 150 days, right? What do you think is going to happen as this plays out? What is this? It's a second generation of infection, a secondary outbreak, right? And here we have some further ones going on. Are these guys from? Have they recovered twice? No, they're probably just residual susceptibles here. Okay, so now we have yet another generation going on. Okay, now I will tell you one vignette here. I mean, I'll just note it commonly. So I did a lot of work with ODE models for many years with mathematical epidemiology, including some at an individual level, using ODEs to characterize evolution of individuals. And I must say that it was a very it was a very eye-opening moment when, having worked with these ODE models in packages like MATLAB or Mathematica, or packages like Vensim, which don't allow you a visual depiction, I coded them up in AnyLogic for the first time. I created them in AnyLogic and ran them. And I immediately saw patterns visually that wiped away a lot of speculation and gave me an understanding about why I had seen certain puzzling features that I had gone down rat holes trying to explain. It just made it immediately clear when I saw visually what was going on. Sometimes that's the case when you use a spatially explicit model. I would note I had a similar experience with a CWD model within the past few years, where we had a CWD model that was an aggregate model depicting things, and then we ran it in a spatially explicit context, and I suddenly saw some patterns associated with the distribution of prions that threw a lot of our earlier work out the window in terms of the fact that there were certain places where the prions were overwhelmingly distributed compared to others based on deer's feeding behavior and behavior in terms of water seeking. That made it very clear that it was not the average prions in an area that were going to be the relevant metric. It was prions in certain places to which the deer were exposed on an ongoing basis. And I hadn't realized just how profound the differences in density of those prions could be until seeing it from a spatially explicit model. So these sort of depictions, while they look interesting and nifty, they actually are very helpful sometimes for stimulating research insight, for helping to correct certain assumptions that you've had. Spatial patterning is as important in my mind as sort of patterning over time in terms of our understanding. So that was the baseline. Let's now go to a short duration of infection, say duration 10. How do you think this will differ with a short duration of infection? But let's say do 5, I'm sorry. How about duration 5? How do you think this will differ for a duration 5 infection? What we just saw. So I'm running it. This time it caught. What do you think will be the consequence of this? Will we see something very similar to the last one with ongoing outbreaks? No. Now we see basically a persistently susceptible population. Why is that? Why is that? Why is there such a difference from the baseline? We can go to 10 as sort of an intermediate example. Why is there such a pronounced difference in intuitive terms? Even 10 seems likely to exhibit this sort of disease-free equilibrium being established quite quickly. Why is that?
Your wave of infection is very narrow.
Your wave of infection is narrow, so there's very few residual infectives to infect that next generation. By contrast, duration 50, what do you think will happen there? What do you think will happen with duration 50? How wide is the wave of infection now? Very wide indeed, right? We have trouble reasoning through this in our head because there's so many factors interacting, and they don't always interact in a linear fashion. They have complex interactions. Now we're seeing these new susceptibles come about, and once again we get a rather different phenomenology. And you'll see here these individuals who are getting infected in this new wave. They're getting infected almost immediately. You don't really see these nice rings sort of etched out over time, but rather you see the generations meshed together. And this goes to one of these points that I was mentioning to Dominic, which is, these models can be very useful for thinking through the consequences of our assumptions when we have the data to pin things down. for doing quantitative analysis that's very specific. You know, this intervention will secure a 10% lower burden of infection over 5 years than this other one. We can give recommendations like that when we have stronger evidence to bring to bear. But when we don't have strong evidence to bring to bear, we can often make some learning in terms of the phenomenology that help us rule out certain hypotheses, that help us rule out, in fact, certain ranges of parameter values because they just don't jive with what we see over time. So if you're dealing with rabies and you're dealing with, you know, spreads and concentric rings of infection, there's going to be certain underlying features of the assumptions that make that possible and certain that do not. And the picture that you see here is just profoundly different from what we saw with some of those other parameter values. In the one case, a disease-free equilibrium being established, and in another case, concentric rings. This is what a physicist would call the phenomenology of it. It's not so much that we can predict exactly when a given individual is infected or exactly how many, but we can recognize broad sort of modes of behavior that can point you to certain features of the situation that suggest certain ranges of parameter values are more plausible, or certain outcomes are likely to be expected. So the phenomenology is pretty important. And in this case, we have three very different phenomenologies associated with the same underlying waning immunity assumptions, but with different parameter values. 5 and 10 on the one hand, the baseline, and 50. 50 leads this kind of miasma of infection circulating with rings that are less easily sort of distinguished, and over time probably a blurring of generational boundaries. Anyway, we've just used this model. We've seen how models can help us articulate theory at the level of an individual and their interactions with others. Remember back to Maine, how we went to Maine and we could set the environment in which people circulate. In Maine, you know, the fact that they have 8 neighbors and so on. We saw how we could, using this sort of theory, we could set up experiments, what-if questions that are scenarios that allow us to investigate the consequence, the logical consequence of our assumptions in a very visible way with respect to certain outcomes of interest for different assumptions. And we saw how we could change those assumptions by defining these experiments in AnyLogic with different assumptions, say, for average illness duration. And then we saw how we could modify the structure of a model in a way that would lead to profound changes to its behavior, but where the phenomenological behavior, the sort of types of behavior elicited from that model, differ pretty significantly for different quantitative assumptions concerning parameters. And here we have sort of the enterprise of modeling writ large, both in terms of investigating quantitatively rich contexts and in terms of theory building and looking to broader types of evidence to help inform our understanding of what's going on. Okay, so ladies and gentlemen, very simple model, much more stylized than any of you are likely to use in your research, but one that's helped us, encounter our first little steps with AnyLogic. My work with you for the rest of the day will be to start to build up these models on your own, to work with them, and to see how we can use them to represent some additional types of texture within your modeling context. But I think for now, perhaps we should have a health break,
Yep.
And we can resume in about 5 minutes or so. Thanks very much.
You have